So question 3 is the diagram shows the atomic energy levels of the atoms in an unknown gas. So we've got the atomic energy levels. We can see that our electrons can jump between. And what we know is as an electron jumps between, it releases that energy in the form of light or electromagnetic radiation, and we can determine whether or not that is visible light, infrared radiation, ultraviolet light. So continuing on the question, predict the shortest wavelength of visible light that could be emitted from the unknown gas. So let's review and see what we're being specifically asked. We want to know what energy level, if we're to jump between, would produce a wavelength of light that is visible, but it has to be the shortest possible wavelength of light that is visible. So we know light is visible. It's given it to us at the bottom here between 400 nanometers and 700 nanometers. But we want the shortest possible. So we want the energy level jump that is close, that produces visible light that is closest to 400 nanometers. Can't be less. It can't be 399. It could be slightly above, but cannot be less, and it's got to be close to 400 because we want our shortest possible wavelength of visible light. So there are multiple ways to go about solving this question. One way would be going through every single energy level and figuring out what type of or what wavelength of light is produced. And that way was done in, I believe, paper 1 for the 2020 paper, where we tabulated kind of our different possible wavelengths produced by jumping between different levels. Here, I want us to work from a different approach. And so think about it, what wave or what energy produces 400 nanometers or a wavelength of 400 nanometers. So we know, going into our formula book, energy is equal to hf, Planck's constant, multiplied by the frequency. We know that frequency is equal to speed of light over its wavelength. So we can substitute that in. And so we know, substituting that in now, E is equal to hc over the wavelength. Let's substitute the variables we know in, which would be h, which is Planck's constant, which is 6.628, multiplied by 10 to the negative 34. I'm just going to throw some brackets in. Then we have 3 times 10 to the 8. That is the speed of light over. Now remember, 400 nanometers is not in the correct units when we're using a constant. Planck's constant has meters in it. So if we were to punch just 400 down here, would be incorrect because Planck's constant has meters as one of the units. So we need to convert nanometers to meters. So the conversion, if you look in your formula book, is going to be times 10 to the negative 9. And there's our formula there. We can punch that in. We're going to get 4.969 times 10 to the negative 19 joules. Remember, Planck's constant has joules as the energy outcome. In our form, or in the question, we're working with EV or electron volts. So we need to convert joules to electron volts. We do that by dividing our joules by 1.6 times 10 to the negative 19. Again, this is a value in your formula book. Get familiar with where it is. That ends up getting us 3.106 EVs. So we need to find a difference between levels that gets us close to 3.106 EVs. Now, the thing to think about is, do we want something greater than 3.106 or do we want something less than? So the way that I would go about thinking about this is, I'm going to throw it in a different color, is using our formula before. E is equal to Planck's constant, speed of light divided by the wavelength. Now, Planck's constant is a constant, same with the speed of light, that's not changing. So I would rewrite the formula as energy is equal to 1 over the wavelength, and we can think of it as a relationship. So if we increase the wavelength, so from say 400 to 401, we increase the denominator on our fraction. And if you increase the denominator, you're going to decrease the outcome. So if we go from say 400 to say a 400, say 450, we increase the wavelength, and we, as a result, will decrease the energy outcome. So we're looking for something that is either 3.106 electron volts or less than. So let's go back up here. I'll clear this out. And let's look for a jump. So 1.3 to 2.7, it's a 1.4, so it's definitely less than, but I reckon we can find something closer. 1.3 to 4.1, it's looking at a 2.8, so we'll keep that in mind, 2.8 EVs. Let's see if we can get something closer. So 1.3 to 5.6, that's 4.3, that's well and truly over. How about 2.7 to 4.1? That's less than our 2.8, so we've scratched that. 2.7 to 5.6, that is a 2.9, it looks like. So the energy difference between our 5.7 minus our sorry, is it the other way around? 5.6 minus our 2.7 is equal to a 2.9. So that seems to be the greatest difference. And that's in electron volts. Let's convert our electron volts now to joules. Before we divided by, up here by 1.6 times 10 to the 19. So here we're going to multiply it by 1.6 times 10 to the negative 19. That's going to get us the joules of 4.64 times 10 to the negative 19 joules. And again, look at this. The energy here in joules is still less than, so it's following the rule we said. Now we've got to find out what the actual wavelength of that light is. Our formula before is energy is equal to hc wavelength. We can rearrange that to wavelength is equal to hc over energy. We can punch that all in. So Planck's constant on top again, 6.628 times 10 to the negative 34 multiplied by 3 times 10 to the 8, which is our speed of light, all divided by our energy. Remember the one in joules because Planck's constant has joules as one of the units. Negative 19, punch that into our calculator, and we end up getting 4 to 8, oh, it's a horrible looking 8, times 10 to the negative 9. Now remember, this is in meters. We can convert this to nanometers, which would be going to your table and you'd notice it's already got, my answer already has the times 10 to the negative 9, so I'm just going to drop that and I get left with my nanometers. So I'm sure if we scroll down a little bit, we have 4 to 8. And that's our solution for question 3.